So my task will be much easier, and I can start defining gravitational wave astrophysics. What is gravitational wave astrophysics, or if you prefer astronomy, but I like astrophysics more? Well, my personal definition of gravitational wave astrophysics is that gravitational wave astrophysics studies the astrophysical characterization of gravitational wave sources, the description of gravitational wave sources, tries to understand them. And it's quite hard to study because there are no books. It's too young and continuously evolving for a complete textbook about gravitational wave astrophysics. But luckily enough, gravitational wave astrophysics was terribly boosted in the last few years. Guess by what? By the detections by LIGO and Virgo. And currently, I would say that most gravitational wave astrophysicists work mostly, but not only, on binary black holes, binary neutron stars, and neutron star binaries. So basically compact binaries. And in my personal opinion, one of the main, or probably the main open question that gravitational wave astrophysicists are facing is what are the formation channels of merging compact binaries. So basically this is the question we will try to address during my lecture, or at least to review the state of the art of our efforts to answer this question. And this is the outline of my lecture, how I will organize our knowledge about this. So first, I will review what we know about the formation of compact objects from stellar evolution and supernova explosions. Then I will focus on binaries of these compact objects. Then I will discuss the dynamics of black hole binaries. You will see in a few minutes why we are talking only of dynamics of black holes and not dynamics of neutron star binaries. And then, if there is enough time, we will say something about the cosmological evolution of these systems, looking for third generation ground-based gravitational wave detectors. So, let's take a step back and start from about 2 years ago. On September 14, 2015, the two LIGO interferometers in the United States obtained first direct detection of gravitational waves. GW150914, that was mentioned many times this morning, and you saw this very same picture that I'm showing, was interpreted as the merger of two black holes. And during this morning, you have learned a lot about this detection and the other detection and why they are so important for physics and science. In this afternoon, we will focus on what astrophysicists have learned from these detections. So what is the importance of these detections from the astrophysical point of view? And first of all, from these now 11 detections, we have learned that binary neutron stars can merge, and when they merge, they are associated with a coercive electromagnetic emission. But I will not go into detail of the electromagnetic counterpart because there will be lectures later on this week where that will be focused on this topic by people who are way more expert than me. But we have also learned that binary black holes exist. Binary systems composed of two black holes. Those were studied for about 40 years or even more, theoretical from the theoretical point of view, but we didn't have a single confirmation of their existence. So theorists studied them for many, many years before the existence of these systems was unveiled by LIGO detection. From this detection, we also learned that binary black holes can merge within a Hubble time, so it's a time that is shorter than the time of the universe. This was something that was not obvious to all theorists. Many gravitational wave astrophysicists say that we would never have observed a binary black hole merging because the life of the universe was too short for them to merge. And then, thanks to at least 7 of the detections, we know that stellar mass black holes can be way more massive than we thought. We know that massive black holes, that is stellar black holes with a mass larger than 20 solar masses exist and can be part of these binaries. This was a big surprise for the astrophysics community because the only black holes for which we had a sufficiently reliable measurement of the mass when GW150914 was first reported were all light. All of them had a mass less than about 20 solar masses. And because also most of theoretical models, astrophysical models of black hole mass did not expect black holes to be so massive. Let's start from this point. So, what are the masses of the compact objects that have been observed by LIGO, Virgo, and by other astrophysical observations? In this very famous cartoon by the LIGO-Virgo collaboration, you see the masses of black holes and neutron stars, not just from gravitational waves, but also from electromagnetic observations. And in particular, in the top, the orange points show the masses of black holes that were observed through gravitational waves. The two, let's say, child black holes and the remnant product on top. But we also see other black holes. The green dots are black hole masses that were measured from electromagnetic observations. Basically, they are black holes in X-ray binaries. And you see that there is quite a trend. So almost all black holes from electromagnetic observations have a mass lower than about 20 solar masses, while if we consider gravitational waves events, many of those guys have mass larger than 20. They cluster approximately around 30-35 solar masses. And then down here you see the, sorry, to switch it on. You see the typical masses of neutron stars ranging between 1 and 2. All of them are from electromagnetic observations, mostly radio pulsars, and then we have the two neutron stars in GW17, 0817, and their remnant. So how do people measure these guys, and why are the green dots so different from the orange ones? Well, here let me show again, in the form of an histogram, the green dot that we have seen before. These are black hole masses from X-ray binaries. And actually I was a little bit more conservative here than in the LIGO-Virgo cartoon, because here there is about 20 sources. I just listed the one for which we have the most reliable measurement. How do you measure them? Well, you first know that there is an X-ray binary, so you know that there is a black hole or a neutron star in there. Then you try to observe the spectrum, visible spectrum of the companion star, and from this observable spectrum you can get a hint of the orbital velocity of the companion star with respect to its companion. In this way you can get what we call a dynamical measurement of the mass, and this is very important because it's the only way with electromagnetic waves to really pinpoint the mass of a black hole. But to get a spectrum of the light of the companion, so to recognize, resolve the companion star, and even get a spectrum of the companion star, you need the companion star to be very, very close to us. Maximum few megaparsecs. And this means that to get this histogram, you can consider only the, really the neighborhood of the Milky Way. The Milky Way and maybe up to the Magellanic Clouds and some very nearby galaxies. In contrast with gravitational waves, you can survey a much larger volume. As we have seen this morning, we are already going to observe objects that redshift about 0.5. And what was our understanding of the mass of compact objects when GW150914 was first published? Well, it can be summarized with these plots. So this was about what we knew about the masses of black holes before gravitational wave detection from the observational point of view, and this is what we knew from the theoretical point of view. This plot shows the mass of the compact object as a function of the mass, initial mass of its progenitor star, assuming, of course, that the compact object originates from a star. It's called ZAMS because astrophysicists call it zero-h main sequence mass. Well, it's just, let's say, the initial mass of a star. And these lines here, with different colors, show different predictions that were obtained before GW150914 was released. Each of these lines correspond to a different metallicity of the progenitor. We will see in a minute why metallicity is important. And you see, with this model that was obtained with the BSE code, there is no way to reproduce the masses of the black holes in GW150914 that are reported up there. So this was the state of the art when LIGO Virgo did their first detection. Although there was a few models that allowed also to produce this kind of mass spectrum of black holes. This plot is the same as before, so we show the mass of the compact object as a function of the initial mass of the progenitor star. For different metallicities of the progenitor star, 0.02 here means about the metallicity of the Sun, and here is about 100 the metallicity of the Sun. And you see that with this other model, we can explain the formation of black holes that are more massive and also account for GW150914. This model was published before the detection, but it was, let's say, not the mainstream. Now let's see why this model can produce black holes with this much range, while the other one cannot. So let's try to see what are the main physical processes that can affect the mass of a compact object. Currently, we think that the most important, say, ingredients when we want to understand the formation of compact objects are the evolution of the progenitor star of the compact object. Here again, we are assuming that compact objects come from massive stars. Then for other exotic things like primordial black holes, of course, it's completely different. So very important is to understand the evolution of the progenitor star and its impact on the mass of the compact object. And this means essentially understanding the stellar winds that I will define in a minute. And the second ingredient is the final fate of the compact object. So what happens when the compact object, the final fate of the progenitor star. So what happens when the progenitor star dies, which happens mostly through a supernova explosion. Let's start from the first point, so progenitor star evolution. Well, I think we all know, if not, we can discuss it later, you can ask me later. Stars evolve during their life. Stars form from the collapse of gas clouds as protostars, then they start igniting hydrogen in their nuclei, and so they shine. And their evolution, both in terms of luminosity, color, duration of their life, and so on, strongly depends on their masses. So in this cartoon, you can see that the life of a star with a mass in excess of 25 solar masses is very different from the life of a star with mass in the intermediate range or for a light star. And basically, the general picture, and probably naive picture, is that if a star has an initial mass between about 8 and about 20-25 solar masses, it evolves and then leads to the formation of a neutron star. If a star has a mass in excess of about 25 solar masses, it evolves in a different way, and at some point it leaves a remnant that is called a black hole. What does produce these differences in the evolution? A very important thing, but I think the most important thing in the life of a star is mass loss. The mass of a star is not constant from the main sequence, from the very beginning of its life to the formation of the compact object. And what changes the mass of a star is the so-called stellar winds. By the way, our knowledge, theoretical knowledge of stellar winds, have completely been upgraded in the last 10 years. surface, which explains why also our understanding of the mass of black holes is changing so fast. What are then stellar winds? Well, this is a cartoon of the atmosphere of a star. In the atmosphere of a star, the photosphere, photons reach the atmosphere and they start interacting with ions that are present in the surface of the star. And these interactions, during this interaction, momentum is transferred to the ions by the photons. If the photons can transfer enough momentum to the ions, then the ions can be even unbound from the surface of the star. And this coupling between the photons and the ions is, of course, pretty much efficient if you have metal lines, because then this coupling happens through resonant metal lines, especially iron lines. And this means that the rate at which a star loses mass by this process called stellar winds depend pretty much on the metallicity of a star. So the bottom line of this is the mass of a star, even of a progenitor of a black hole or a neutron star, is not constant during its life. It changes, and it changes because the star loses mass through a process that is called stellar winds, and these stellar winds are due to the coupling between the photons emitted by the star and the ions that are at the stellar surface. This coupling is way more efficient if there are metals at the surface of the star. And here I would like to add a caveat. What are metals and what is metallicity for astrophysicists? Is something that is completely different from the definition of metallicity from the rest of the world. So for astrophysicists, metallicity is just every element heavier than helium. In particular, you will see many times in my slide that metallicity is quantified with this capital Z letter. Usually redshift is named with a small z, while metallicity with a capital Z, and is defined as a fraction of an element heavier than helium. So basically, if m is the total mass of a star, then x is the ratio between the mass of hydrogen and the mass of the star, y is the ratio between the mass of helium and the mass of the star, and z is the sum of the mass in all the other elements over the mass of the star. And these are the values that we expect for our sun. So our sun is a 73% mass fraction hydrogen, 25% helium, and only 2% metals. So these metals are the one that drives the mass loss. And then what is the dependence of mass loss on metals? Well, usually astrophysicists describe the mass loss of a star as something which scales to the metallicity to alpha, where alpha is an index that has been uncertain between about 0.5 and 0.9 for many, many years. Recently, some updates of this theory have shown that the value of alpha is more close to 0.9. So the mass loss of a star is pretty strong function of the metallicity. Unless what? Unless a star is close to its Eddington limit. What does it mean? We can define the Eddington luminosity of a star as the maximum luminosity that it can emit before the radiation pressure is no longer balanced by gravity. And we can define the Eddington parameter gamma as the ratio between L star, which is the current luminosity of a star, and L Eddington, which is the Eddington luminosity of a star. And if the gamma parameter gets very close to 1, the star is pretty much radiation pressure dominated, which means that it loses way more mass than it would have lost if it were basically equilibrium star. So if the star is radiation pressure dominated, the dependence on the metallicity is no longer very important. The star keeps losing mass just because it is radiation pressure dominated, so just because its radiation pressure is dominating over the gravity. And then we can describe the index of the dependence of mass loss on metallicity as alpha, which is 0.85, at least according to the most recent work, if the star is no radiation pressure dominated, so if gamma is less than 2/3, while this dependence goes basically to 0 if gamma is larger than 2/3, so if the star gets close to be radiation pressure dominated. And then from this very quick overview of stellar wind theory, we can draw the evolution of the mass of a massive star, and we get something like this. This is the mass of a star as a function of time for 7 different metallicities of the star. So the same initial mass, 90 solar masses, very massive star. And then let's evolve the star with 9 different metallicities. Each of these models loses mass because of stellar winds, but you see that the solar metallicity star, which is the red one, at the end of its life has lost more than half, basically 2/3 of its mass. While the metal poor star, with a metallicity of 500, the solar metallicity, basically ends its life almost with the same mass as it has at the beginning. And I forgot to mention that this point on the right, where the curves stop, is what we define the pre-supernova point. So when the star, in the star, nuclear burning is over and the star is about to die. So why am I telling you this? Is this a course of stellar astrophysics? Oh no, I don't want another course of stellar astrophysics. I'm gonna tell you this because the final mass of a star and the way it evolves to this final mass is tremendously important to determine what is the post-supernova evolution of a star. Basically, the final mass of a star and the final mass of its core are crucial ingredients to understand the mass of a black hole and a neutron star. And this is something that has become increasingly clear in the last few years. So I showed you this plot of the evolution of the mass of a star with time, just to compare what we get with current models and what we obtain with models of 10, 15 years ago. So here I consider a star with a solar metallicity. The dotted line here is obtained with recent models. The dashed line here is obtained with older models, and the final mark, the triangle or the square, shows the pre-supernova mass. So the triangle is the pre-supernova mass in the recent theory, and the square is the pre-supernova mass in the, let's say, old theory. Here you don't see much difference, but here we are at solar metallicity, and for solar metallicity the theory has not evolved so much. If we consider a value of the metallicity that is 1/10 the solar metallicity, we find a pretty much large difference. So here you see that for a star with initial mass of 110 solar masses, the triangle, so the new theory, predicts a final mass of about 50 solar masses, while the square, so the old stellar wind theory, predicts a final mass of about 15 solar masses. So a huge difference. Yes, please.
My question is, the starting points of this plot, the initial mass, is an arbitrary choice, or it comes from somewhere?
Oh no, well, of course we can start from whatever mass we want, at least up to 150 solar masses. Above this mass, only few stellar evolution model can really give a reasonable answer. Here I just selected 4 possible masses to give you an impression of what happens for an intermediate mass star. Things basically do not change with the old model. Massive stars and very, very massive stars. So So basically, this gives you an idea of something that evolves in a neutron star. This gives you an idea of what evolves into a black hole, and this gives you an idea of what evolves into a pretty large black hole or something else, as we will see in a minute. But in principle, I can do this trick for every possible mass.
The minimum should be like, for neutron stars should be 8, something, yeah?
Yeah, and I don't have time to talk about it during this lecture. The treatment of electron captured supernovae in binary system can change it a little bit. So let's say that for single star, 8 is reasonable number to keep in mind, but binary evolution can play dirty trick also from this point of view. Okay, I think I've already discussed this. So we say the bottom line of showing you this is that, okay, the evolution of a star is something pretty complex because it depends on stellar winds, and the final state of the star before it undergoes the supernova is crucial because it will determine the end of the supernova too, the development of the supernova. So let's now discuss what we know and mostly what we do not know about supernovae. So this is a very rough scheme of the stellar interior of a massive star around the end of the life of a star. You know that the star starts burning hydrogen in its core, then some of them switch on helium burning in their core, then possibly carbon and heavier elements. By the end of nuclear burning, the star looks like an onion with an internal iron-nickel core, then some outer shell of silicon, oxygen, neon, carbon, and unless they have lost them completely because of stellar winds, also a helium and hydrogen shell. Well, when a massive star develops an iron core, then iron group atoms have this very peculiar feature. They have maximum binding energy. So this means that no more energy can be released by nuclear fusion. And then the star runs out of fuel and the core starts to contract, collapse, till electron degeneracy pressure can stop the collapse, but only if core mass is below the very famous Chandrasekhar mass, that is about 1 point something solar masses. But if the core is above this limit, then electron-proton capture removes also the electrons, so basically you run out of electron pressure, and this means that we face also a further collapse, a collapse to nuclear density. Nuclear density, neutron degeneracy pressure stops the collapse, and you have the process called as formation of proto-neutron star. Here starts the problem, because up to here the physics has been worked out quite well, but here we have a problem. So how can this process of collapse leading to the proto-neutron star develop what we call a core collapse supernova? Well, we have the binding energy of the core. The binding energy of the core can be as large as 10 to the 53x. So this is a huge amount of energy. But how can I use it to launch the shock of the supernova, so the supernova explosion? This is a problem because let me say first that the genuine mechanism triggering and evolving a core collapse supernova is unknown. So there are many models, all of them involving some slightly or very different physical processes. But the truth is that we have not understood core collapse supernova. This is a big problem in models of compact object formation nowadays. I will just briefly discuss here what is the most popular, the first and the most popular model of supernova engine that has been proposed, which is the so-called convective engine. The basic idea of the convective engine is that we have the potential energy of the core. This potential energy is converted into thermal energy, which is mostly thermal energies of neutrinos. And this allows the core to bounce, driving the shock. On the other hand, the shock must be sufficiently powerful to reverse the collapse of the outer layer. Let me try to make it clearer with a cartoon. So we have the core that is already collapsed, where the protoneutron star had formed. Then we have a very high density region where the neutrinos drive their energy flux outward, so the shock starts propagating. But then we have also the outer part of the star, the outer layer, that do not have not felt the shock again, so they are imploding on the central part. And there will be a region that we call shock stalling region, where the density of the material becomes sufficiently low that the neutrino starts to leak out, so they cannot propagate the shock anymore, and the shock stalls. And this is a problem because when you reach this shock stalling region, your shock will not evolve any further, and so you cannot really launch the supernova. How can you overcome this problem? You can find it more carefully explained in this review by Chris Fryer. But let's just try to show it briefly by looking at this cartoon. In the convective engine model, what happens is that at the surface of the protoneutron star you have the onset of some convective cells, convective bubbles, that can help the energy flux to reach the outer layers, overcoming the shock region. And in this way, in some of the models, you can actually launch the supernova. I say in some of the models because this convective engine, the fact that the convective bubble can lift the shock and revive it above the shock stalling region, this happens only in some of the hydrodynamical models of supernova. But not all supernova, hydrodynamical models of supernova are successful in undergoing the explosion. And this was proposed, well, there has been a lot of debate, so why not all the hydrodynamical simulations of a supernova succeed? It may be because we don't have the right physics when modeling the supernova, or it may be that indeed, in some stars, the supernova does not succeed. And this idea, the latter one, was proposed by Chris Fryer in 1999 and Fryer and Calogera in 2001. They proposed that in some cases, the supernova shock has to stop anyway, and the supernova will fail. So not all massive stars will have a successful supernova, but in some of the massive stars, the supernova will fail. When does it fail? The idea is that if the bound mass of a star in the pre-supernova stage at the onset of the shock is too large, then the supernova can fail. This is something that Fryer and Calogera demonstrated with some more sophisticated model, but you can verify it, well, at least try to understand it with a very back-of-the-envelope calculation. So you can try to connect the pre-supernova mass, we can try to connect the pre-supernova mass with the final fate of the supernova. And in particular, according to this calculation, you can say, okay, I have a given energy which is available during the supernova. This is the energy that I have available during the supernova. Let's put it equal to the binding energy of the envelope. So this is the binding energy of the stellar envelope, where Mn is is the envelope of the star, M core is essentially the mass of the core, so you can think it is the mass of the protoneutron star that forms, and Rm is the radius of the envelope, so the radius of the star just before the onset of the supernova. If I put numbers in here, I will find what is, if there is any, what is the maximum mass of the envelope, above which the supernova cannot succeed because the supernova energy, the maximum energy that is available for the supernova is not sufficient to unbind the envelope. So with this very rough calculation and assuming that the maximum energy available for supernova is 10 to the 51 erg per second, and that 10 to the 51 erg, this is wrong, and that the envelope radius is about 10 solar radii, which is realistic, I get that if the envelope of the star is more massive than about 50 solar masses, then it is extremely hard for the supernova to succeed.